Okay, let me go briefly over the reasoning behind this Bernoulli trial simulation. This is problem 4 in the current activities that we're doing, and I just want to have this as a record so you can refer to it. All right, so what we're talking about when we're doing Bernoulli trials is we're considering simulating a series of what I'll call doctors, and each doctor is conducting operations. Now, these operations are called trials. So each doctor has several trials, and we'll assume that they're all doing trials at the same time at the same rate. So here it says trial index. That just means that this is the first trial, second trial, third trial, and so on. Now, there's an acceptable success probability. There's an acceptable failure probability. Which is P. So for this doctor in particular, he has failure probability P, failure probability P, failure probability P. And each operation is going to have success or failure. He'll have some successes and some failures, but his failure probability is P. Now this doctor, for some reason, his failure probability goes up. And we'll assume it goes up to P1. And that could be for a number of reasons. Maybe there's something wrong with his lab, something wrong with his instrumentation, something wrong with his procedure. And so his failure probability goes up. Suppose for this particular doctor it goes up at this point, and for this doctor it goes up at this point. So the question is, can we detect these changes? Can we detect if a doctor's failure probability is increasing to P1 just based on the doctor's record? And the way to do this is hypothesis testing. We can consider what we would expect if the doctor's probability is fine, and what we would expect if the doctor's probability goes bad at some point during the trial. Now, we don't know where in the trial his probability goes bad, if at all. So we have to consider the possibility that it could go bad anywhere. So we want to compare the probability of what we see, the observed result, given that it goes bad somewhere. It goes bad somewhere. And we take the ratio of that with the probability that the observed result given that he doesn't go bad. Okay, so there are two options. So we're looking at his record and we say, what's the probability of this happening if he went bad somewhere during the trial sequence? And we're going to divide that by the probability that we get the result that we saw, given that he's fine, that nothing went wrong. Okay? This is called a likelihood ratio. And there's some theory behind this, but this is the right way to distinguish between these two cases. Now, every time you run this experiment, you're going to get a ratio. And of course, if it does go bad, it will kind of weight the probability towards this upper, and if it doesn't go bad, it will weight the probability towards lower. But since it's probability, of course, there's nothing certain. So you might get some sequence where he has a lot of failures, even though he didn't go bad, and there's nothing wrong with his procedure. Or you might get a case where he goes bad, but he's lucky, and his operations work out. But the point is, we want to detect as many as possible. We can't detect the outliers, but we want to detect as many as possible. And the way to do this is to construct this likelihood ratio. This is called the statistic. And then you set a threshold, which I also call a cutoff, for the likelihood ratio. Now, if the likelihood ratio is large, we would expect that he went bad somewhere. If it's small, we would expect he didn't go bad somewhere. So we set a cutoff that says, okay, if the likelihood ratio is bigger than this cutoff, we'll reject the null hypothesis. The null hypothesis is the hypothesis that he doesn't go bad, he's fine, there's nothing that we need to do. And if his ratio is too large, we reject that and say, well, we better look into this. Maybe there's something wrong with this doctor. Now, on the other hand, if his likelihood ratio is less than the cutoff, we don't reject the null hypothesis. We leave him alone. We say, well, it looks like he's fine. We'll keep watching, but we're not going to do anything just yet. All right, so that's the theory behind it. So I'm going to, in the next video, explain how the different subroutines or functions that you've created are relate to this scenario and how we're going to use these to evaluate Bernoulli trials.